All right, today we're going to round out our understanding for convergence. And what we've been doing, we've been talking about when a function converges for what values of x. For example, we've said for values of x in between -1 and 1, or in other words, if a function converges for the absolute value of x to be less than 1, -1 to 1, uh, we want to know a little bit more about its convergence. In other words, we want to know where will it converge at the endpoints. So I know, yeah, I know that if a function converges in between -1 and 1, I know that for the absolute value of x greater than 1, it does not converge. But the question is, what happens when the absolute value of x equals 1? What happens at the endpoints? So we're going to be testing the endpoints of the convergence to see whether or not a function converges there or not. Um, and we're going to learn some new methods for finding this, and this will round out all of everything we need to know about convergence of functions using polynomial approximations. Okay, so let's start off with a sort of the simplest idea. If a function is monotonic, monotonic means going in one direction. Monotonic means it's either always increasing or always decreasing. Um, and the function is bounded. So if the function is bounded, um, then there is a great criterion that we have for determining um, the determining whether or not the endpoints are part of the bound. Okay, so here is the criterion. It's called the convergence criterion for a bounded monotonic sequence. It says if a sequence a sub n is bounded and monotonic, bounded meaning it will uh, bounded means the limit as n approaches infinity of a sub n equals some number L. If it's bounded and monotonic, then it converges to some finite limit L. So that talks about the sequence. So it's saying that A of n will reach some limit L. All right, well, how does that help us? So right now we're just talking about sequences, and then we'll extend this to series. So we've got our first example. It says the following sequence, A sub n. Um, well, A sub n is n over n plus 1. It's bounded and increasing, thus it must converge. So let's talk about why is it bounded. Well, this function, the limit as n approaches infinity of n over n plus 1, we know that that's going to equal 1. We could use L'Hopital's rule to get that. Um, you'd end up with 1 over 1, which equals 1. So it's bounded. And as n increases, we also know as n increases, a sub n is going to increase. Think about that. Like when n is 1, we'd have 1 over 2. When n is 2, we'd have 2 over 3. When n is 3, 3 over 4. So it's getting close to 1, and it's always increasing. So the fact that it's bounded and increasing, it means that the sequence must converge to something. Here we have a divergent sequence right up here. Uh, that value is increasing for all values of n. So as n gets bigger, so does b sub n. But it's not bounded above. It's not bounded above because the limit as n approaches infinity of n squared over n plus 1 equals infinity, or the limit doesn't exist. It doesn't approach some value. And lastly, we've got this another divergent sequence, and this is just this oscillating -1, 1, -1, 1, -1, 1. And the reason that this, going back to our original criterion, it needs to be monotonic and converge. Well, in this particular case here, uh, it is bounded. It's bounded between -1 and 1, but our function is not monotonic. It's not increasing always. So it is not divergent. So in those three examples, A through C, those are looking at sequences. But if we wanted to extend this to series, to whether a series is convergent, oh, whether a series is convergent or divergent. Let's first start off with a series with non-negative terms, so all positive terms. We need to see not whether the nth term is bounded, but we need to see if the partial sums S sub n is bounded from above. In other words, the sum of all those n terms must reach some limit. And if it does, then we will be converging to a set value. Well, in order to test for a series, what we can do is we can use integration. Um, so, we can think about some function f of n, and this function f of n is um, let it be a decreasing continuous function that has positive values for f of x for all x greater than or um, equal to 1. So the infinite series would be the sum of all of these values. And so the way that we can think about the sum of all those values, our calculus way of talking about sums is we can look at the integral from 1 to infinity of f of x. And if that integral converges to a value, then my series will converge. And if this integral diverges, then my series will diverge. And just to add some clarity to this idea of using an integral as opposed to the sigma notation, we know that the sigma notation from n equals 1 to infinity of f of n, that's adding up from, when n is 1, n is 2, n is 3, n is 4, all the way up to infinity. Well, we know that this is going to be less than the integral, which is adding up all values, any value in between 1, 2, 3, 4, 5, like all the what's in between 1 and 2. Well, there's tons of numbers in between 1 and 2. So the integral is going to be bigger than the sigma notation of f of you know n dn. So because that integral is bigger, if the integral converges and the integral converges and the integral is bigger, then the sigma notation must also converge because it's less than. So it's an interesting idea there, and written in a slightly more formal proof here, which says the sum of the n terms must be less than, using the logic before, the first term plus all the subsequent terms from 1 to n, and that the first term plus the sum of all terms from 1 to n of f of x dx must be less than the first term plus the integral from 1 to infinity of f of x dx. And this integral here, if it's fixed, if it converges to L, then what we got there is that the nth sum, the sum of the nth term must be less than, so the sum of the nth term must be less than the first term plus the limit, and the limit, we're talking about L, we're talking about the convergence of my function f of x dx from 1 to infinity. So therefore, if we can show that this integral converges to some value L, then we know that the series will converge to a number. Well, let's use that integral test to show that the harmonic series 1 over n diverges. Well, just to get up what does 1 over n look like? Well, s sub 1 would be 1 over 1 s sub 2 would be 1 over 1 plus 1 over 2. S sub 3 would be 1 over 1 plus 1 over 2 plus 1 over 3. So that's what this harmonic series looks like. But to use the integral test to show that it diverges means that we need to show that the integral from 1 to infinity of 1 over x dx, we need to show that that diverges. So we need to use uh, what we know about improper integrals, and we could say, well, this is the limit as x, let's not use x, as a approaches infinity of 1 over a, the integral from 1 to a of 1 over x dx, and then, take that integral, and we know that this equals the ln of x integrated from, or evaluated from 1 to a, and we need to include that our limit, that this is the limit as a approaches infinity. Continuing on, it's kind of a messy ln of the absolute value of x. So this equals the limit as a approaches infinity of ln of a minus ln of 1. Well, ln of 1 we know is just 0. That's going to go away. And the ln of a as a approaches infinity, well, that approaches infinity as well. So this limit does not exist. It approaches infinity. Therefore, we know that our harmonic series diverges. And we prove that using the integral test, which we just introduced. Well, that harmonic series that we just looked at, 1 over the sum of 1 over n, is part of a really important class of series called the P series. And the general form for a P series is the sum from n equals 1 to infinity of 1 over n to the p, where p is some positive number. In other words, we're ensuring, by p being a positive number, we're ensuring that it keeps that rational feature. If p were negative, then like if say p were -4, 1 over n to the -4 would be really just n to the 4, which gets rid of its rationalness. So by ensuring that p is greater than 0, we continue it to be a rational function. And therefore, we could say, let's let f of x be 1 over x to the p, and we want to talk about the integral test now in general. And we get this nice rule here, and I'm going to redevelop that. We're saying the integral from 1 to t, where we're letting the limit as t approaches infinity of 1 over x to the p. As long as as long as p doesn't equal 1, this is going to equal, well, it's going to equal x to the negative p plus 1 all over negative p plus 1 evaluated from 1 to t. And when we evaluate that from 1 to t, evaluating that from 1 to t, we get that this equals x to the negative t plus 1 minus x to the negative p plus 1 all over negative p plus 1. Made a mistake. That x should be a 1. And we'll continue with this in the next video.